If we start with our reductive amination, so if we're going to make an amine, so some kind of nitrogen structure with a bunch of carbons coming off of it, whatever those R groups may be. If we pull the most common method, which is looking at the reductive amination, we can start off with just ammonia and do a reductive amination where we form the amine and then reduce it down, and we add on an R group. Okay, so I'm going to start coloring these in. We add in a red R. So our product now has this red R. We can then do this with a second reductive amination. Okay, except in this case, what we'll go through and do is we'll add in a purple R. Okay, so we've got a different R group, and that's one of the primary reasons why we would go through and do this method, is that we can then put on different carbon chains onto our amine. Okay? We can go through and do this a third time. Go ahead and stick with the blue. And we can put on our last, or second to last R group. Let's make sure I'm getting my colors kind of right. Okay? And now all three of those R groups can be different, or they could be the same. All of that's going to depend on what carbonyl I go through and start with, or I react that amine with. Okay, so depending on what we want, we may want them all the same, we may want them all different. You'll notice for the very last step, we don't do a reductive amination, which seems a bit weird. Why do we not do a reductive amination? It has to do with our hydrogen presence. In the case of doing all of our reductive aminations, the first thing we did was formed our imine. Whoops. With our carbon and then our R group. We had to form that imine with some number of hydrogens, and then we reduced that imine. Can a tertiary amine make an imine? No, it doesn't have any hydrogens to make the amine. Okay, so what we'd end up doing is kind of stalling out this weird intermediate, and that wouldn't work very well for us. Okay, so we'll just go through and do a standard alkylation. I'm not sure that green shows up well. It kind of shows up. Okay, so we can put on our final R group, okay, as our green R group. And remember all our colors: red, purple, blue, and green. So we now have all of those substituents. Okay, well, one question that might come up, if we can alkylate at the end, why did we not alkylate from the very beginning? Right, this wasn't a slide. I hand drew this one on Monday. What's the issue with trying to alkylate from the very beginning? Keep all of our pieces. If we start with just the standard amine, and we try and alkylate right from the get-go, sure, we've got a reasonable nucleophile in our nitrogen with our amine, kick off our halogen, and we would have alkylated it. Okay, we'll have to deprotonate as well, lose a hydrogen. And we'd have our primary amine, except the issue that we run into is that we still have that lone pair, which means that lone pair can now react a second time or a third time. So if we're going to try and run a standard substitution reaction, a standard alkylation, okay, with just starting ammonia with an alkyl halide, we can't control the products. We can get primary products, secondary products, and tertiary products, and potentially quaternary products all in the exact same reaction bath, okay, which means our yield for any one of those, whatever we were trying to target, is going to become relatively minimal. So what we want to be able to do is selectively target each and every single one of those possible options, particularly if we wanted different R groups attached. If we want different R groups, just adding a standard mix of random carbon alkyl halides is going to be a horrible choice, because we're going to get an even larger mix of possible products. Okay? So that is why, we go through and do these reductive amination steps to generate our primary amine, controlled secondary amine, controlled tertiary amine. And since the very last step, there is only one nucleophilic site, and there can only be one nucleophilic site, because after we alkylate a fourth time, there's now no nucleophile. So I don't have to worry about a second alkylation reaction occurring. I'm already at the end. Okay? Kind of makes sense? Yeah.
So if you do go to the primary amine with your purple carbonyl, the first one you did,
Yeah.
why did it just stop? Why did it only add one? Why, if you end up with the primary amine on the bottom left, you do still have a lone pair. And if you had that, wouldn't it attack it again? Why would it only add the one R group?
Reactivity in each of those cases is drastically reduced. So once you've got that carbonyl, you're going through a sequence. Yes, there is still carbonyl left, but if we look at a preference now for reactivity, there's a much larger steric effect that now prevents that from reacting a second time, at least as cleanly. So we will still run into this issue with making some of it, but it's a much smaller amount because we have to go through more steps to go through and make it, as opposed to just a direct substitution.
Do you just add the largest groups first if you wanted to add R groups on?
Sure. Okay. And actually, sorry, I'm going to switch up on that. We go through that process to make the primary amine. When is the primary amine formed? After we do the reduction. Okay? When we start the reduction, there is no more carbonyl left. The amine can't do another amination because we don't have an amine. We have an imine, which won't alkylate, won't react with the carbonyl. Does that make sense? That's a much better answer to your question. My hand wavy make up an answer.
So once it's the imine, then it's done.
We've lost its nucleophilic character. Okay. Once it's the imine, we've now turned our structure into being an electrophile at that what used to be the carbonyl carbon, our imine carbon, and we no longer have that nucleophilic character. Okay. Questions? Okay. Our aryl diazonium salts. So we went through the mechanism on forming the diazonium salt at the end of this, or at the end of Monday's lecture. And we said one of the things that you could go through and do is that we now have a pretty phenomenally good leaving group in the form of nitrogen gas. Okay, so if that nitrogen just takes the electrons away, we end up with our straight up nitrogen gas with its lone pairs. And that leaves what charge behind on our carbon? A really positive charged carbon. Okay? It must be forced off. It can't just leave on its own. But we can force that off by reacting it with some magic reagent in between. Okay? That magic reagent to facilitate this has to be a copper salt, and it will be some kind of copper halide most commonly. Okay? But you can see it with a couple other possible nucleophiles as well. And that's what this slide was. So if we do copper bromide, copper chloride, copper iodide, okay, all of those will go through and do a substitution. We'll kick off the nitrogen gas, and we'll end up with our halogen attached to the structure. Okay. All of those, I believe, since we love named reactions, I think are Sandmeyer reactions. It happens to be the name. I think they're called Sandmeyer reactions. Whoops. Okay. Don't quote me on that, but I'm pretty sure that's right. Okay. I'm about to talk about that. And that one shows up in the study guide, which is why I'm adding it. And then we can also go through and do it with a cyanide. I don't think that one gets classified as your Sandmeyer. The Sandmeyer is exclusively with the halogen substitutions. Okay? We need the copper there to help facilitate the electron transfers between this because we generate that benzene cation, which is incredibly unstable. Okay? So we need to kind of stabilize and mitigate those transition states. The last one on there I wrote as H3PO2. I didn't have time to draw a figure, but the result of this is thoroughly exciting. Is that? What happened? Yeah, we did a substitution, just like we did with the others, except our substitution was a hydrogen for the N2. Okay? We're busy playing around in the tutoring center among the tutors, trying to find a mechanism for that. Could not come up with a clean mechanism for it. Okay, I will tell you that the only reference that we found was a radical mechanism. Okay, so it's ugly one way or another. Okay, so if you happen to go through and form the diazo compound, if we react that with H3PO2, we can then kick off that whole nitrogen group. We could lose that. Okay? And that's going to become kind of nice because how can we go through and make that diazo compound? Well, our last reagent was NO2 minus and HCl, okay, which came from our amine. How can we make an amine? It was HCl and some metal, iron, tin, zinc, mercury, all of those, from the nitro group. And we could get our nitro onto our ring. Sorry, ran out of space. That's a benzene ring. Using nitric acid and sulfuric acid. Okay. So the reason why this becomes interesting is I can put on a nitro group. Where does the nitro direct? Our meta positions. So I now have a director to a meta position on that ring. Okay. I can then reduce the nitro group to the amine. Okay. Now I've got an orthopara director. So I can change the direction on that ring depending on what reagents I'm using. We can take this a step further. If I then go through and convert it into the diazo compound, I can remove that entire nitrogen directing group altogether and take it right back to where I started. Okay? So this can allow me to put on substituents in various locations in ways that seem nonsensical because the directing group is no longer present on the ring when I look at the final product. Okay? And you will see a question like this in the ACS study guide where they go through this reagent sequence. Because you end up putting on a couple different substituents and you look at them and say, well, how can they be meta? Say if we had a bromine and a methyl group. It doesn't make sense to have that meta arrangement because both the methyl and the bromine are orthopara directors. So how could they possibly get oriented meta to each other? Okay. To do that, we could go through some arrangement with these. Okay. Putting on the nitro group and then converting it all the way through these other sequences of steps and end up kicking it right back off at the end. It allows us very careful manipulation of where we can put those substituents. So it's kind of neat as far as the EAS reaction goes. Questions? Unfortunately, or fortunately, depending on your perspective, you don't need to know the mechanism for any of these, okay? Because they're kind of difficult. That first one, in theory, already knew. The second one, you don't need to know. That last one, you also don't need to know. I doubt they would ever ask a direct mechanism question about it. We showed it, but you didn't need to know it. And our very last one with our H3PO2, you don't need to know that one at all. Okay. You might see a question about, is it a radical mechanism versus a standard ion mechanism? But that's highly, highly doubtful because you're looking at a very, very specific question to one particular reagent that rarely shows up. Okay? So the odds of seeing that are pretty limited. Questions on anything on that slide?
Previously, I thought you had H2O in the position where you have H3PO2. Would
Yeah,
H2O be the same thing?
No.
No.
No. Yeah, it needs to be hypophosphorus acid. This is not a typo. This is H3PO2. Okay? It needs to be that structure because that's what's facilitating the reaction. The H2O shouldn't do it. Okay? I don't remember what the H2O was associated with.
That H3PO2 has a charge?
No, it is not charged. H3PO2 is neutral. Okay. Very odd looking structure too if you wanted to look up the Lewis structure. Other questions? Okay. What else can we do with them? Well, our diazoniums, as you might guess, are positive, which means they are pretty good electrophiles. They also happen to be aromatic, which is where our most common usage of them comes from. We can react them as an electrophile in an EAS reaction. Okay, so what they're showing here is a brief sequence, skipping the sigma structure intermediates to show the EAS net result. Okay, so our phenyl compound acts as our nucleophile in our EAS mechanism. We generate our intermediates that are resonance stabilized, which then goes through, we lose the hydrogen and we get our tied systems. Okay? That results in that diazo, actually, how do we call these? I don't remember what we call them. Regardless, the product that we get, even if we can't come up with a name of them, is that we now have a massively conjugated pi system. That massive conjugation of the pi system is what allows for the absorption of visible light. Well, if visible light is absorbed, that's going to change our product from being just a white crystal where no light was absorbed, to now certain wavelengths being absorbed, we now get colors coming out of our compound. So depending on what substituents are on those rings or how many rings we have, we will see varying colors come out of it. So this is one of the things we talked about. You can get some pinks, purples, browns, and some kind of orangey yellows, okay, coming from these compounds. Okay, so kind of neat in that respect, but that's pretty much it. Questions? Yes, tweet.
Diazonium zone are good electrophile.
Yes.
That we mean both arine and alkene. Arine and alkene. I mean the ring without the ring, right? The NH2 group connecting to benzene.
That's an amine. That's not a good electrophile.
No, I mean this one. Okay. Oh.
Yeah, the diazonium salt. So our diazonium salt is in our purple circle now on the boards.
Oh, that one.
That's our diazonium salt. Why would that be a good electrophile? Why is the diazonium salt a good electrophile? It is positively charged. What charges our electrophiles? They're positively charged. Okay. That's kind of an interesting question, which kind of come back to you in just a second maybe. Which nitrogen is our electrophile? The one with the lone pair is the electrophile, which sounds very, very odd. Why is that odd? It's the one that's not positive. How many electrons are around our positive nitrogen? 8. Okay. Can it accept more electrons? No, but what it can do is steal some electrons from the other nitrogen. If it steals those electrons, what happens to our endmost nitrogen? It becomes our positive. There's our electrophile. Similar thing happens. Okay, we keep coming back to this example. How does this compound react? H3O+. What does it act as? An acid. What's our definition of acids? Proton donors. We have to have a positive hydrogen. What's the most reactive atom in this? It's the hydrogen. That's why it's called an acid. But when we look at the structure, we say, oh, it's the oxygen. Why? Because it's the one holding the formal positive charge in our Lewis structure. So that allows us to zero in on the chemistry there. And our chemistry has to occur somewhere around that positive charge, but that does not mean that that atom is going to act positive. Okay. What we have to decide is, can it act as an electrophile? Well, for it to act as an electrophile, what does it need to do? Accept electrons. Can the oxygen accept electrons? No. So it can't act as an electrophile. So what we do instead is say, where can it get electrons from to neutralize that positive charge? It can steal them from the hydrogen, giving us the H+. There's our Bronsted-Lowry acid. There's our activity. Same thing is happening with our diazonium. We see the positive charge in our central nitrogen. Can that central nitrogen act as an electrophile? No, because its octet is already satisfied. It cannot accept more electrons. So what we then do is say, okay, what electrons can I move around it to get it happy, okay, to neutralize it? And that's where we can shift those pi electrons over, and we can identify that our nitrogen can act as our electrophile, okay, or our other nitrogen acts as the electrophile. Okay? Yes, Tui.
Does it have to be a ring connecting to that double nitrogen or not? This part, or can it be anything?
To be an aryldiazonium,
Yeah.
it has to be a ring. Aryl means ring.
Which one?
Aryl. So diazonium salts, when they are aryl, will act this way.
Okay, but if not,
Okay.
then
If not, they can act similarly. You're going to see similar situations, but they're less common
okay.
to show up because they don't generate the brightly colored solutions that we would hope to get out of
So
these.
it has to be aromatic.
To get the bright colors,
Okay.
yes.
Thank you.
Okay. Yay, last slide. I think it's the last slide. It is the last slide. All right, what this one is our Hoffman rearrangement. It shows up a lot in the study guide. So some students have asked about it already because they've been working through and seen it show up. So we're going to go ahead and look at that mechanism just because it looks a bit crazy and talk about some kind of interesting features of it. What we're looking at is the presence of an amide. So we've got our carbonyl with our nitrogen. Okay, and I'm going to intentionally leave these hydrogens over here. All right, and what we're going to do is react this with Br2 in the presence of KO, and I've got R in parentheses. We're going to come back to what that R means as we push further through this mechanism. But ultimately what we have is O minus with some R group attached to it. Have we seen this sequence of reagents before? Br2 and OR minus? Yes, we have. Where have we seen this sequence of reagents before?
That would be a bromonium ion and a
No, we aren't going to get bromonium with an OR minus. Where we saw this was when we first started talking about the alpha carbon reactivity to carbonyls. Okay? And I'm going to take a guess that that's actually how this reaction sequence was discovered. Somebody built some amide structure and said they wanted chemistry at that alpha position. They wanted to put in a halogen, maybe put a double bond there, get a conjugated pi system. That was their goal. So they said, hey, I know how to do that. I can put in bromine. Gives me an alpha bromine at that position. I can do the elimination. Great, I now have that conjugation. So they mixed everything together, and they got an entirely different product and said, what the heck happened? Okay? That's where I think this reaction probably came from. Okay, so let's kind of work our way slowly through this. What's the most reactive thing present here? The OR minus, that's our negatively charged species. What can that act as? Base or a nucleophile. Which is more nucleophilic, nitrogen or oxygen? What does a nucleophile need to do? It needs to donate electrons. Which element is more willing to donate electrons, nitrogen or oxygen? Nitrogen, because it's less electronegative. Which means if our OR acts as a nucleophile and comes in and attacks, we kick out N minus. What does N minus do? Come back in and kick out the OR minus. Okay? So our OR minus is not going to likely act as a nucleophile. It's going to be acting as a base, okay, as its primary chemistry. This is where things get tricky. When we did this with our alpha carbon, we said our alpha carbon was acidic. Why was it acidic? Next to the carbonyl, we had resonance stabilization. Right? What about the amide? Those amide hydrogens. Okay. I looked at them and said those aren't acidic, so I tried to do everything at the alpha carbon and couldn't get the same results that they got. Okay. So what does that mean? If we can't get the result that's supposed to come out of this by making that first assumption, what does that mean about the assumption? It's wrong. Okay? So my assumption was wrong. The next thing I went through and did was looked up a table of pKa's. pKa's measure what? Acidity. What two pKa's do you think I looked at? The pKa of our alpha carbon hydrogen or our amide nitrogen. Guess what the pKa's are? Virtually identical. Okay. Neither of them are particularly acidic. Okay? You're both looking at, or both of them are pKa somewhere up in the 20s. Okay? But they're both relatively the same. So if my assumption to go through and work at the alpha hydrogen didn't work, then I'm going to have to change my assumption and go to the other one. What happens to our nitrogen now? Negatively charged. It's got a lot of electrons hanging out on it. Okay, which means that nitrogen is now what? Very nucleophilic. Okay, or very basic. Okay, well, if it's basic, we don't really go anywhere. We end up just shuttling hydrogens back and forth. So let's see what happens if it acts as an electrophile, or sorry, nucleophile. What's the nucleophilic atom? Carbonyl carbon gives us resonance to stabilize that negative, which explains why it's acidic. Looking at a second molecule is a possibility, but there's another electrophile present. Br2 is an electrophile. The electrons come out and pick up our bromine. Oh, I was attempting to draw this so that I could fit it all on here. Yes, that looks incredibly weird. That's one of the reasons why this reaction works. Okay? What happens now? What happened to that hydrogen? That last hydrogen on the amide. That hydrogen is now more acidic than it started. Why is it more acidic? Because the bromine is now attached to it. So that's now a stronger acid, which means more than likely what happens? We get another deprotonation.
Is that OR or
OH. Oh, yes, that should be OR. Sorry. At this point, it needs to be OR.
Sorry.
Did I draw it OR earlier? Yes. Okay.
Yeah.
Please remind me of that in case I miss it again. I will switch it in a little bit. Okay. And our nitrogen is now negative yet again. There is some resonance stabilization with that carbonyl, but we're looking at something that's incredibly reactive. How weak or strong is that nitrogen-bromine bond? What do you guys think? Strong bond, weak bond? Why should it be a weak bond? Bromine's an exceptionally good leaving group. So bromine can start to take those electrons. The problem is that nitrogen then would lose electrons. So we end up going through this really goofy system where our electrons from our nitrogen share inwards. But if we share inwards, what happens to our carbon? Sec. Too many bonds. We have to break a bond. What bond would we break? Pi bond sounds reasonable, but then we're just going to go through this cyclic system of really nothing happening. Eventually what happens? Okay, I know this looks ugly, so give me a second to draw it ugly. I'm going to maintain the relative orientation of all of our atoms. Almost. And then our new bond there, new bond here, and our bromine is kicked off as a negative charge. Everybody see that? So nitrogen shared a pair of electrons to make a pi bond to the carbonyl carbon. That carbon then has too many bonds, so we have to break a bond. The bond we end up eventually shuttling off, okay, regardless of how we exactly look at this mechanism, will be the carbon-carbon single bond. That does a rearrangement, because what we're doing is now shifting that carbon group over to the nitrogen. When it shifts over to the nitrogen, we've formed our second bond. But now the nitrogen has too many electrons. So what do we have to do? We're going to have to get rid of some electrons. That's where our halogen comes into play and takes the last remaining pair of electrons away from our nitrogen. What we've just done is what's known as the Hoffman rearrangement. Okay, so let's clean up our structure a little bit. Okay, and I'll highlight our new bonds again. I added a carbon. Okay, there's our cleaned up structure. Nitrogen still has a lone pair. Our oxygen still has a bunch of lone pairs. Everybody see the cleaned up version from the ugly version? Okay, now what happens? Well, you look at that structure. What do you think? Stable? Unstable? Unstable. Why is it unstable? That carbon in the middle is attached to two very electronegative elements. Okay? Not particularly happy with that system. Okay? So it is now extremely electrophilic. So what can happen? When we go back into our solution, do we have a nucleophile? We still have OR minus floating around. Actually, nitrogen does not want to be negative, so it can pick up a hydrogen from solution. I know this is everybody's favorite move, but we'll just say we added H+. We have those two new bonds formed in this result. Okay. At this point, our reaction effectively stalls. Okay, we still have that carbon, probably even more positive than it was before, but there really isn't anything our structure can do to alleviate that strain. It's kind of stuck in that position. Okay? So here's where things switch. What happens if instead of it being an R, our R equals a hydrogen? Okay, so if we redraw that structure, where R is now a hydrogen. What functional group do we have on the end there? Okay. Got to be a little bit careful. Is it going to officially be a carboxylic acid?
Probably not.
No, because we still have the amine connected to it, so it's some kind of weird cross hybrid. But what would we expect the acidity of it to be? Really, really high. It should be higher than an acid because that nitrogen is electronegative as well, withdrawing some of that electron density. So we would expect that to be relatively acidic. Well, what solution were we in? A basic environment, and now we'll go through and show this again. We now have OH, because I said our R group was an H, picks up the hydrogen. But then our oxygen has too many electrons, so it says, let's share them. But then our carbon has too many electrons, so it says, peace out. The result is that we end up now with a negatively charged nitrogen. We go, oh, that's an awful thing to have. Why would we ever do this? What else is produced? CO2 gas. How stable is CO2? Extremely stable. That's why it's such a problem for us to deal with as far as environment goes. Okay, we can pick up a hydrogen again from solution. I don't care where it comes from. We can call it, maybe even our acidic hydrogen from the beginning, I'll just call it B. And we end up with our final answer with a primary amine. Okay. Interesting results. Number one, we made a primary amine with no contamination of secondary or tertiary amines. Okay, because the nitrogen never acted as a nucleophile. So we don't have to worry about secondary or tertiary amines popping up in this. The other interesting result, what happened to the number of carbons?
We lost the carbon.
You lose a carbon in the process of this reaction. So we end up with a primary amine and we lose one carbon. Okay, which is also interesting in and of itself because most of our reactions are driving to do what? Add carbons. Very rarely have we ever seen situations where we can remove a carbon. Okay? We've got the decarboxylation and we now have the Hoffman rearrangement. Okay? Big old ugly and nasty. Everybody have copied down what they want copied down out of this so I can simplify it. Ultimately what you need to know, everybody said yes to that, right? Not the neatest erase job. But that's what you need to know. Okay? And in particular, we actually have to add one caveat to that. This is only if R equals hydrogen. If our R does not equal hydrogen, we end up with that product. Okay? We can't do the decarboxylation, if you will, because we can't break the bond between the R group and our oxygen very easily. That's not going to happen. So it has to be a hydrogen to be able to be pulled off. Okay? Crazy chemistry. Most rearrangements are kind of crazy and out there. I would highly doubt that very many people were actually able to predict that a rearrangement was going to occur for anything that we've seen when it comes to rearrangements. They tried to do some chemistry, everything went AWOL, and they tried to figure out why it did that. Is it all? Here it is. It's a rearrangement. Now everybody has to memorize this. Okay? Sorry, that's just kind of the way it works.
So bromine's just a catalyst?
Bromine is technically not a catalyst, because for it to be a catalyst, we have to reform Br2 at the end. We don't reform Br2. We form Br minus. Okay? Questions about the Hoffman or anything else? Okay, at this point, we are done with new material. Wasn't too bad. I said I was going to take 45 minutes, somewhere about there. Okay. I have no more new material, so I'm actually going to